This video I want to talk about net force and how we come up with equations to sum the forces. And so net force just means total force or sum of the forces. And another way to write this is this sigma F. Sigma means sum. So these are three other ways to say net force. And I'm going to talk about this with respect to this guy pulling a box, and this box does not move. And so if we draw the free body diagram, let's think that this is a very heavy box. You're going to have a big force of gravity. Force of gravity, remember, is the weight, which is the mass times the gravitational field strength. These are other ways to say force of gravity. We have the normal force. This is the support force going upward. And then we have the right force. This is the force of tension. And because this is stationary, that means I am in static equilibrium, meaning all of my forces are balanced. So I need to have a backwards force of friction, FF. What we really want to do now is come up with an equation that talks about the net force, or F net. Now, we can't just sum all of the forces in all of the directions. We actually have to sum the forces in the x direction and separately sum the forces in the y direction. And so the way that this looks is you go sigma Fx. So the sum of the forces in the x direction. This is going to be our x direction. This is going to be our y direction. The sum of the forces in the x direction, if anything is going this way, we'll call that positive. So I'm going to say that this is the positive x direction. If anything is going that way, we'll call it negative. So there are only two forces in the x direction. That's going to be the force of tension going in the positive direction and the force of friction going in the negative direction. So this is our net force in the x direction. Now, if this is in static equilibrium, or the forces are the object is stationary, we know that it's not accelerating. The sum of the forces in the x direction will be equal to 0. And this is where we're going to leave this right now. We sum the forces in the x direction, then we sum the forces in the y direction. We'll call up positive. So we have the normal forces in the positive y direction, and then the force of gravity is in the negative y direction. Again, this is in static equilibrium, meaning all of the forces are balanced, so the sum of the forces in the y direction will equal 0, and this is where we'll leave this right now. For the next worksheet that you have a bunch of free body diagrams, and all you need to do is sum the forces in each of the directions. So we'll do one more. Let's say I have a box and I have a triangle on that box, and I want to sum all of the forces on the box. First, I draw my free body diagram. I have the force of gravity on the box. I have, let's say the triangle's really heavy. The force on the box by the triangle, and then I have a large normal force. Now this gets to the heart of why this normal force has to be really large, because this box is stationary, meaning it's also in static equilibrium. So the net force, or the sum of the forces on that box, is going to be equal to 0. So if I sum the forces in the y direction, we'll call up positive, I get the normal force minus the force of gravity on the box minus the force on the box by the triangle. This sum of the forces in the y direction, again, is going to be equal to 0. So when we look at this, then we can pull the force of gravity and the force on the box by the triangle to the other side. What we're left with then is that the normal force is going to be equal to the force of gravity on the box plus the force on the box by the triangle. Now, if we were to put numbers in this, let's say the force of gravity on the box is 5 newtons, and the force on the box by the triangle is 7 newtons, then we would know that the normal force has to be 5 newtons for the force of gravity on the box, plus 7 newtons for the force on the box by the triangle. So that normal force is going to be larger. That normal force in this case will be 12 newtons, not just 5 newtons, not just equal to the force on the box by the Earth.